Hello, this video is titled Plane Curves and Parametric Equations. Now, we're going to look at a new way to sort of represent functions. Instead of your standard y equals f of x that you're used to, obviously y is the dependent variable, x is your independent variable, so that means y depends upon x. Suppose that x and y separately are functions of a new variable, which we call a parameter, so it's another new variable t. So in other words, t is the independent parameter slash variable, and then x and y are both two different functions of that t. If you're looking at, say, projectile motion applications in physics, and with y being the height, x being the range, that means the height was a function of range. Using this, you can find them independently, that just where it's a function of t, which would be time. So you can find the vertical distance without even knowing what the horizontal distance is. So this pair of equations is called parametric equations with parameter t. The graph is called a plane curve, denoted by generally variable c. Now, these curves, represented by parametric equations, they indicate the orientation direction of the curve as t increases. So instead of just a graph, it sometimes will show the direction that it's moving as t increases. Let's just take a look at an example here, and the graphing calculator can do this. This one's kind of easy to do manually, and the arrows just represent the orientation, which way it's going. So normally when you make these t charts, you're picking a value for x and then calculating y. Well, here we're putting in a value for t and then getting the xy coordinate based on the value of t. So if I put in -2 into these two equations right here for x and y, I'll get -3 and then 2, which will be right up here. I just arbitrarily chose -2. Theoretically, the graph would go on and on forever, so wherever it started in this case was irrelevant. Sometimes something might specify the values of t. I guess if t was obviously representing time, in a certain example, we would start at 0. So you put in -1 into these equations right here, and you'll get -1, -1. There's that point. Put in 0, you get 1, -2 right here. And then put in 1, you'll get 3, -1 right there. And then you put in 2, you'll get 5 and 2. And then there it is. Now in the standard graphing calculator, come up here, clear all that out, and I go to mode. Oh, it's already in parametric mode, so I must have been doing something. So function mode is just regular, normal y equals a function of x. Parametric, that's what we're doing right here. Parametric, so I put it in parametric mode, then you go quit. And then when you come over to the y equals, see it lists the equations as a pair of equations, x and y, as a function of t. And it's allowing for more than, 1. So, and the button right here next to the alpha that you normally hit when you're putting in variable x, when you hit that same button here, it will now use t instead of x. So let me double check these. It's 2t plus 1 and t squared minus 2. So I'll go 2, and I'll hit where that x is. It'll now be t plus 1 t squared minus 2. Now, of course, how much it will graph will be based on, what values you tell it here in the window. But I'll see it starting at 0 here. I'll go -2 to +2, kind of like we had already done there. So I don't think you have to worry about the step here. But the min and the max, that's way too far apart. So I'll just go like -5. Well, actually, don't need to go that far back. and 5. Of course, I can go back and adjust this. I'll go negative 5 to 5, like so. Oh, come down here. And then now I'll hit graph. And there we are. Now it looked a little flatter than mine because you see this is, I have the y, I don't know what I have for the scale of the y here. Maybe it's just from negative 2 to positive 2, so kind of made it look flatter whenever the new graph, but it was correct. And the direction that it graphs it also shows the orientation. Now, suppose that we want to convert a rectangular equation over to by eliminating the parameter and converting it, take a parametric equation and convert to a rectangular equation. So from parametric to rectangular by eliminating the variable. And of course, you can go the other way around too. So what you want to do is use. Oftentimes, there's more than one correct way to do this. This one, x equals 2t plus 1. Solve for t, and I want to solve for t in terms of x. I don't want to do that for this bottom one because I don't want to have a t squared. Now, the next example, I will do that, but that'll be a different reason. Because I don't want to get a plus and minus square root. You know, I want one unique solution here. So if I take this top one, solve for t in terms of x, I'll have t equals x minus 1 over 2. Easy algebra. Then you just plug that into the other one. So here's where I put t, and I didn't bother to expand anything out, nor do I think you would be expected to do that either. So if t is now x minus 1, I have x minus 1 over 2 squared minus 2. So you see this equation here in pink is now a rectangular equation because it's just y's and x's. Let's take a look at this next one. Now this one, I did solve for t squared, but I didn't take the square root of it. Notice that. That's what I don't want to do. I don't want to get, because it would have two solutions, plus and minus. But I want to solve for generally the smaller power. I guess that's the way to look at it. Solve for the smaller power, unless they were equal powers, and it wouldn't matter. So I didn't need to take the square root of this, because if I knew that I was just going to go from t squared to t to the fourth, I could just square both sides. So if t squared equals x over 2, that means t to the fourth would be x over 2 squared. So this is actually another parabola. So then y would just equal x over 2 squared plus 1. Now parameters don't have to be variable t. You know, they often are here, but this is still considered a parametric equation. It's just that your parameter is theta this time instead of t. But really the same thing would have applied. You see, when I graphed it in the calculator, I just used the variable t that automatically is, when you push that button, it produces a t. So that doesn't matter that it's theta, in other words, really. So this kind of problem, you don't really solve like we did up there. You don't solve, not because it's a letter theta, it's because of the trig functions. You don't solve for the variable in terms of, don't solve for the t or the theta. When you have cosine and sine, you have to go with this Pythagorean identity right here to do this. So we don't solve for one variable in terms of another. In fact, this one is not going to be a function. So we have to, it's going to, it won't be a function, y as a function of x. So I just let cosine equals x divided by 3, and sine then would be y over 7, and then just substitute it right into there, and that gives us the ellipse. X over 3 squared plus y over 7 squared equals 1. And then I graphed it in parametric form. Just use t, and then there's your ellipse right there. Now here's another one. Okay. X equals 4th root of t. And y equals 8 minus t. Of course, the domain, here would have to be t greater than or equal to 0. So I'm not sure what this part's right here because it's over here. Let me get rid of that. But anyway, so if you raised both to the fourth power, you would have x to the fourth equals t. This is an example of one that I'm showing you that would work. You could actually do it one way or the other. So solving for t in terms of x gives you t equals x to the fourth, and you plug in the other one, and you get y equals 8 minus x to the fourth. That's fine. Because we didn't take a plus and minus square root. It was not necessary here, so that's why that's okay. Now the other one, I just solve for t here, and I get t equals 8 minus y. Then you plug it into the first equation, so x equaling the fourth root of 8 minus y would also be correct. Either one of those two answers is correct. All right, so I graphed this one. Now we're going to look at finding parametric equations for rectangular equations. In other words, this time it's rectangular. I mean, it's parametric, then we're going to convert it to rectangular. No, backwards. It's rectangular, now I'm going to make it parametric. So this one, these simple ones like y equals 2x squared, you want to let one of them just equal t, and you want to pick the more complicated side. So this one's actually really easy, because if you let x equals t and plug that in there, if x equals t, then y would just be 2t squared. And then there's your set of parametric equations right there. Now the next one, y cubed minus 4 equals 2x. So this one I did both ways just to show you. And if I let x equal t, so I put t into the right side, and then bring the 4 over, so I have y cubed equals 2t plus 4. Therefore, y equals 2t plus 4 to the 1/3. That would be one. So with x equals t and y equals 2t plus 4 to the 1/3, that would be your pair of equations. Now this one, let y equal t for right here. So you have t cubed minus 4 equals 2x. And you have t cubed, then you have t cubed minus 4 over 2 will equal x. So that's also correct. Now one interesting thing about this is if you put the same values of t in there at the same time into both those equations, they won't yield the same point. So it might seem that something's wrong. It is not, because even though the same t may not yield the same point, what's going on here is that you will have different t's, but they'll yield all the same x's and y's. For example, for this first pair right here, if I put 30 in there, I'll get x equals 30, and then I'll get the cube root of 64, which is 4. So for the one on the left, when t equals 30, you have the point 30 comma 4. Well, for that other equation to also be correct, it must have a value for t. It does not have to be the same value that will generate the point 34. So if you look at the other pair of equations, if you put in 4 for t right here, and then put 4 in there, you get 64 minus 4, 60 divided by 2 is 30. So you'll get that same point, 30 over 4. So you're hitting this point, but at different values for t into each one. And that just goes on forever and ever and ever. Every point's going to be covered, but they'll just be covered by different t's. So they're both correct parametric representations. Now for these kind of equations, x squared plus y squared equals 25. And then if this is actually circular, but it could be ellipse also, but you just kind of take the square root of 25, and which is 5, so you just let x equals 5 cos t, y equals 5 sine t. And then, of course, that would give you put them in there, that's 25 cos squared plus 25 sine squared, which does equal 25. I guess I didn't really, that is a circle though. Didn't hit the zoom standard. Actually, I guess I could plot this one real quick, couldn't I? Let's go over here. x equals 5 cos t, y equals 5 sine t, delete all that. Okay. All right, now let me go to the window. I'll just go 0 to 2 pi. Obviously, that'll take it all the way around there. So 0, which it will convert 2 pi to decimal. And actually, the 5 is pretty good. I may, that's going to be right on the edge of it when I graph it. I may change that to 6 just so it's not. Yeah, let me change those to 6s just so it's not hitting the edge of the screen. Not that that's a big deal, but. So, yeah, so this, it looks like an egg there, an ellipse, but now I'll just go to zoom, command zoom square. I said zoom standard a minute ago, zoom square. That kind of squares it up. There we go. So it's still a circle, but now it actually looks like one. So I think I'll paste this much nicer looking picture in here. Yeah. Well, of course it looks like an egg there, but I'll take care of that when I move it over here. All right, there we go. Okay, do not worry about any of these. I just found these kind of interesting. These are just actually graphs, just that happens to have names to them. I have no idea really the history of them. Although prolate cycloid, that sounds like some medical condition that I probably have and don't know or something. Yeah, doc, my prolate cycloid's flaring up on me again. Anyway, hypocycloid. Oh, these are ones sometimes when I'm teaching a face-to-face class, we'll just kind of, just for fun, put in a couple of kind of equations and see what they turn out to be. Some of them don't turn out to look like much. Sometimes they look like you're just scribbling an ink pen on a piece of paper, but I don't know. I thought this one kind of had an interesting shape, so I kept this one. And this one I really liked. A student came up with this one, and then I liked the way it did the spiral there. I thought that was pretty neat. So, all right, not important. A hypotrochoid. All right. Well, that was exciting. And that is the end of this video on plane curves and parametric equations.